Hello and good afternoon, everybody. Thanks for joining us for this webinar on cathodoluminescence spectroscopy for geological applications. My name is Kamran Khajepur. If you don't know me, I work as microscopy product manager with AXT. For those who aren't familiar with us, we are the largest independent distributor for high-tech scientific instrumentation in Australia and New Zealand. We have an extensive product range covering microscopy, microanalysis, nanofabrication, nanotechnology, and life sciences. It's been always our pleasure to bring cutting-edge scientific and analytical tools to facilitate your research, and we continue to do so. One such example of our suppliers is Delmic, who pioneered two highly innovative microscopy platforms involving light and electrons. They are based in Delft in Netherlands. We've been working together for almost 2.5 years now and installed the first comprehensive Spark system at Monash University in Melbourne. Please have a look at our website and make yourselves familiar with our product range and services. Today, the topic is Spark and its geological applications. Spark is the most sophisticated and featureful CL detection system in the market at the moment. We covered its general aspects and applications in our previous webinar. I hope you guys know about this. If not, you can easily access the recorded version of the webinar from our website and watch it at your leisure if you wish. And hopefully with your feedback and questions, we can actually make these webinars more useful for you and tailor it to your specific needs and research field and applications in future. Before getting to the presentation, I'd like to mention that you can raise your questions easily with typing it in the QA part in the bottom of the screen. And those questions will be answered during the webinar by Tone, our presenter. So this moment, I'd like to introduce our today's presenter, Dr. Tone Coynan, who some of you may know because he's been in Australia once and gave us a few very, very nice actually presentations on similar topics and also at the previous webinar. So Tone is Delmic's in-house Spark specialist, and in fact, the person who designed the Spark platform. He obtained his bachelor and master's degree from Utrecht University in Netherlands. He then completed his PhD at the Foam Institute Amolf in Amsterdam in 2014, where he developed the Spark platform and did investigate the nanoscale optical properties of various metallic structures. He now works at Delmic, developing novel cathodoluminescence applications and improving the Spark platform as a whole. So I over it now to you, Tone, and I hope you guys all enjoy the webinar today. Over to you, Tone.
Yes, thank you, Kamran. Good morning, everybody. I'll start my presentation. Yes, so as Kamran mentioned, today's topic is about cathodoluminescence imaging for geology. And so here's a brief outline of what I will discuss. And so I will briefly introduce the cathodoluminescence process in rocks. And then I will continue to explain how you detect cathodoluminescence and how you should prepare your samples in order to do proper CL imaging. And then I want to show a couple of applications in the field of geology and how CL can be applied to that specific field. And I want to end with an outlook. So cathodoluminescence, the process itself starts with an electron beam, and typically this electron beam can be in an electron microscope. And in this electron microscope, you direct your beam towards a material where it interacts with that material. And because the electron beam packs a lot of energy, there are a lot of processes that occur simultaneously. For example, And there's emission of secondary electrons and backscattered electrons, which can be used for regular electron microscopy. But there's also emission of electromagnetic radiation, and this spans a large frequency range because the electrons that come in are so energetic that the electromagnetic radiation that is generated ranges all the way from the X-ray regime, so very energetic radiation, all the way to the infrared. And so in the spark system and in cathodoluminescence, you focus on the electromagnetic radiation that is emitted from the ultraviolet to the infrared. And so this is what you do when you do cathodoluminescence spectroscopy. And I briefly want to explain how the cathodoluminescence process works in rocks, because I think it's useful to have a little bit of background in that direction. And so when your electron beam hits your material, it starts to decelerate inside of that material, and there are a lot of collisions with that material where the electron transfers energy. When that happens, it collides with the electrons that are in the material itself. And normally, when the material is at rest, these electrons are in what is called a ground state, and so nothing really happens when they're in the ground state. But when they are excited by this incoming electron beam, these electrons are promoted to what is called an excited state. And after a while, the electrons they fall back into their equilibrium ground state. And when they do that, they have to release energy, and this sometimes happens with the emission of a photon. And this is the cathodoluminescence emission that you observe. Now, it's important to note that because the primary electron beam has so much energy, you can create a lot of light packets, photons, per primary electron. And so this process can be quite efficient, and so you can have thousands of photons per primary electron, making it quite efficient process in some cases. Furthermore, the volume in which this process occurs strongly depends on the primary electron energy, so the acceleration voltage that you set in your electron microscope. And so if you increase the electron energy, you have a more efficient excitation because you inject more energy, but the volume will also be larger, which means that the spatial resolution is reduced a little bit. And so this is a trade-off that you have to deal with. Now, rocks are typically insulating materials, which means that they have wide band gaps. And to briefly explain that, so the band which represents, say, the equilibrium state of the material, and the band which represents the excited state of the material, the conduction band, are separated quite far apart by 5 to 15 electron volts. And to put that, say, in a little bit of perspective, that means that if the excited electrons decay directly from the conduction band, they really emit light in the deep UV or the extreme ultraviolet. And that's something that is difficult or not really possible to observe when you have a CL detector. But nevertheless, you do see a lot of light emission at lower frequencies, higher wavelengths. So in the blue, red, green part of the spectrum, and in the infrared. And so why is that? And this is because defect states, they play a very important role in rocks, and they're normally the dominant factor in determining the CL emission. And what these defect states do is that they make intermediate states in between the conduction band and the valence band, which means that the energy steps become smaller, and the energy of the photons that is emitted shifts from the ultraviolet into the visible or infrared. And so there are many different types of defects for every mineral or rock type, and they're roughly subdivided into two categories. The first one being intrinsic defects, and these are, as the name says, are really intrinsic to or can be intrinsic to a pure mineral, and they can be, for example, vacancies where an atom is missing in the crystal lattice of the mineral. Interstitials where one of the atoms is actually in the wrong place in the crystal lattice. Dislocations where there's a dislocation in the crystal structure. All of these things, they can create defect states inside of this band gap and can lead to cathodoluminescence emission in the visible, as I will show later on. Now, these defects, they really arise from the growth process of these materials. And so as such, they can also be linked sometimes. But they can also be induced by damage processes. And in this case, you should think about maybe stress or compression related to tectonic movement, for example, or heating. But also radioactive decay can be a damage mechanism for crystal lattices. And so both of these, or all of these things, can contribute. So that is one category. The other category is what we refer to as extrinsic CL emitters or defects. And these are foreign dopants. And so they're materials that are not native to the mineral, but they're there nevertheless. And they can be very dominant in the perceived CL response. And so these include rare earth ions. They're very efficient, like europium, terbium, or transition metals like manganese, chromium, titanium are very well known strong CL emitters in some minerals. But this can be quite a complex interplay between dopants. And so some dopants, they are efficient cathodoluminescence emitters themselves. Some of them enhance cathodoluminescence emission from other dopants, and some of them quench the emission from other dopants. And so when you interpret your CL signal, you have to be careful not to misinterpret it, because it can be, all of these things can be present in your material. Now, maybe to briefly compare cathodoluminescence to other SEM-based techniques. And so in electron microscope, you often do secondary electron imaging, where you really look at the surface topography of your material. You can look at the backscattered electron detection, in which case you really look at the density of your material. You can distinguish heavier from lighter elements. In EBSD, you can even access the crystal structure and the crystal orientation. And in WDS and EDS, you're looking at a higher energy range, where you're probing core transitions, and with those you can establish the elemental composition of your material. Cathodoluminescence is more mixed in what you can see, and so you can see or you're sensitive to composition, but also to crystal structure, to dopants, and to defects. And so that means that this is a very versatile and powerful tool, because you can access all of these things. In some cases, it's also a little bit difficult to disentangle all of these different things. So what is the thing you are looking at? But even if you completely disregard the origin of the cathodoluminescence, it gives a unique contrast when you're imaging compared to other SEM-based techniques. And even that is already very interesting, because you can see textures and features in your samples that you cannot see with the other techniques. And as such, it's very complementary, I would say. So this is maybe a good time to ask if there are any questions. I'll have a look. Let's see. Yeah, I don't think there are any questions for now. Yeah, please feel free to ask any if you have any in the Q&A box. But then I will continue now with the CL imaging part. Oh, there's one question. And so the question is it possible to quantify defects? Yeah, this is a very good question. It's also an elaborate answer. And so the number of defects can be quantified in some cases, but as I mentioned, you have to be sure that there are no other things affecting your measurement. And this is quite difficult in a mineral sample, because it's difficult. You don't have any control about how it was grown, and so it's difficult to know in advance whether this is possible. but especially if you combine with other techniques, it can be quite quantitative. In terms of establishing which defect you have, it is quite quantitative, because specific defects have particular emission spectra, and you can often quite accurately identify which defect you have in your rock without a doubt. And so but it can be quite challenging to establish how much of this defect you have. All right, let's see if there are any other questions. Yes. Oh, another question is whether if you do quantification, whether a standard reference material is required. I guess that could be useful, but the reference material should be very similar to the rock you're looking at, and so maybe a problematic thing would be that you would need a lot of reference materials in order to properly quantify your samples. But if you really focus on one particular type of to have reference materials, also to understand which defects are present, because not everything is documented in literature, and so sometimes you can discover defects yourself if you do this properly. All right, so now we'll continue with the, oh no, there's still one more question, which there's a, okay, thanks. I will continue with the CL imaging. And so this was also discussed more elaborately in the previous webinar. So if you are interested, please revisit that webinar. And so our CL system, very briefly, consists of two parts. It has a collection part inside of the electron microscope chamber. So this is the electron microscope here. And a detection part, which holds all the light-sensitive detectors. And so to briefly summarize, say, the strengths of our system, one, the alignment procedure is very accurate, simple, and it is very efficient. So it means that you can collect all the light, and that means that the imaging is either faster, or you can reduce the probe current that you're using, or the acceleration voltage. And from the detection side, we are also very, very sensitive, but also very modular, and so you can, you can do many things there as well. It's good to know maybe that our system is an add-on for commercial SEMs, and as such it can be mounted on many SEM types and versions. All right. So the most important CL imaging types are intensity mapping, in which you raster scan the beam over your sample. And so for every point you collect an intensity with a single pixel detector, such as a photomultiplier tube. And in front of this photomultiplier tube, there can be filter wheel. And so you can either let all the colors go onto the detector, which is called panchromatic cathodoluminescence imaging, or you can color filter it with maybe a rather coarse color filter to get some wavelength information or color information. And so when you raster scan the beam, you acquire, say, an image point by point for a particular wavelength. And then if you would change the filter wheel to a different position, you could collect another image for another wavelength. And in that way, you could reconstruct, say, what is called a data cube with three-dimensional cathodoluminescence data set. Similar to what you have in WDS or EDS measurement and X-ray imaging. The advantage of this type of imaging is that it can be very fast. The dwell times can be shorter than 10 microseconds, which means that you can do video rate imaging and very quickly scan your sample, because it's not always clear what you want to look for. or maybe you first want to identify a region of interest, and this is a very useful way to do that. Furthermore, the field of view that you can have in this mode is quite nice. And so you can have you can scan in one go at least half by half a millimeter. And if you would move the stage, you could scan even more. But with the electron beam, you could scan that much area in one go, which is quite nice, because in geological materials, the feature sizes can be quite large from SEM perspective at least. Then complementary to that, you have hyperspectral imaging. And in that case, the light is directed towards a spectrograph in which you have a diffraction grating, and the diffraction grating decomposes the incoming cathodoluminescence into different colors and projects that onto a pixelated camera array. And this pixelated camera array then measures the spectrum in parallel, and it can do so with a very high spectral detail. So you can measure very nicely emission spectra with better than 1 nanometer spectral resolution if desired. And so you reconstruct the data cube in a different way. So for every point you have a full spectrum, and that way you build up your data cube. And so compared to the intensity mapping, there are some drawbacks in the sense that it is a little bit slower. The cameras that you use you cannot read out so fast, and so the dwell times are typically 15 milliseconds or so, and sometimes a little bit faster. But this is roughly the order of magnitude. And then if you also have a little bit of smaller field of view, which is related to the optics that is required to do such a measurement. And so this is typically more suitable to really study a region of interest, unless you have a way to do stage scanning, which is something that we can also do for some SEMs. Now, for I also briefly want to discuss the sample preparation. And so typically you start out with a natural rock, and this you somehow have to process for SEM imaging. And so what works well for CL imaging is, and which is also quite common for other techniques, is to have a thin section, which is polished, or to have a polished plug or something that is embedded in resin. And so if you have a nicely polished surface, that will improve the results. It does not have to be as nicely polished as you require for EBSD, for example. But a little bit of polishing can greatly improve the results, particularly if you really are interested in fine textures and zonation, for example, in minerals. This can be important. In SEMs, you also require a certain degree of conductivity, and some rocks are not really conductive. And so in that case, you need to coat them with a little bit of carbon or metal. And there you have to take care that the carbon or metal layers are not too thick, because then you block all the light. And so there's a trade-off in the thickness. But you can have a thickness which is still enough for a good transmission, but also good surface conductivity. And another approach is to have a SEM in which you can increase the chamber pressure to do environmental SEM. And in that case, you can also mitigate charging effects, and you can get rid of the charge more easily from the surface. Okay, I'll go back to the Q&A. And so, yes, one of the questions is whether angle-resolved cathodoluminescence would have an advantage in attempting to measure defects. And this is, yes, a good question. It's not something I cover in this webinar, but I can answer it nonetheless. And so I think this is particularly interesting if you also couple it to polarization resolved measurements. And the reason is that some defects, they have a particular orientation within the crystal. And so you can imagine, particularly if the if a mineral or rock was exposed to a particular stress or strain, you can have defects that are aligned in a particular direction. And this is something that has an effect on the angular profile and also particularly on the polarization. And I think this is one of the novel things that could improve and increase the scope of CL experiments, and you can get more out of your system that way. Another question is what the typical thickness of a coating would be. And for carbon, that would be 20 to 30 to 40 nanometers or so, if you have amorphous carbon coating. For metal, it's wise to not go above 10 to 15 nanometers, because the metal is much more absorbing or reflective than carbon. And so the skin depth in metal is about 10 to 15 nanometers. And so if you go beyond that, all the light is blocked. So this is... so moving back to the applications. And so the first application that I wanted to discuss is sedimentary rocks. And sedimentary rocks are studied a lot in cathodoluminescence. And I show here some examples of sedimentary rocks that are well studied, also because they are relevant for the oil and gas industry, but also beyond that for understanding geological processes in general is very interesting. And so to briefly describe what happens in these different sedimentary rocks. And so in sandstones, you have a very robust cathodoluminescence emission, and you have a luminescence that mostly originates from intrinsic luminescence in the quartz and feldspars that are normally present inside of these rocks. And then in carbonates, you have a lot of extrinsic luminescence from dopants, typically. And in carbonates, you have to be a little bit more careful when you do SEM and cathodoluminescence imaging, because the material is more fragile, and you can alter it with the electron beam. And so it's wise to do some tests where you test the current and the acceleration voltage that you're using, and the effect on that it has on the material. Because it can be more fragile. And this is also, this is one particular case where you can benefit from having a very sensitive cathodoluminescence detector like the Spark, because you can reduce the beam current that you're using and the damage that you are inducing in your material. And then for shales and siltstones and mudstones, of course, SEM-based techniques are very popular because the feature sizes are so small, and then, this is also the case for cathodoluminescence. Of course, this more mixed, and so sometimes you can have a rainbow of colors in these types of materials, and there are also a lot of clay minerals present often, and those are quite dark in cathodoluminescence because they're rich in metals. And that those quench the cathodoluminescence emission, but again, having a sensitive system, you are still able to see interesting things there. Now I want to zoom in on the sandstones because I have some nice examples of those. And so here's a really canonical example of how you use cathodoluminescence in sandstones and in quartz-based systems. So this is quartz sandstone, and in the SEM you can recognize different sand grains that are compacted together. There's some pore space also here. And so if you look at the SEM image, it's quite uniform. And so you would guess maybe that these are individual grains. But if you make a panchromatic cathodoluminescence intensity map, you see that there's a lot more structure to this than you would guess initially. And so you see actually that there's a crystal grain which is cracked into a couple of pieces, and this is a hard, high quality detrital quartz grain, but it's cracked, and then it was infilled with another type of material, and in fact this is quartz cement, which has a similar atomic composition. It also has a little bit similar density. And so it's difficult to image that properly with SEM or with backscattering. But because the defect structure inside of the material is very different, it gives a lot of contrast in CL. And so you can clarify that even more when you make a hyperspectral image of a particular area. And so we zoomed in on this particular area in this case. And because you have a hyperspectral image, you can visualize the cathodoluminescence intensity at different wavelengths. And then that is depicted here. And so here the CL intensity is shown for 425 nanometers, which is blue light. You can see that the pore is completely dark and the grain is bright. But then if you move to red light, 650 nanometers, you see that the material that has infilled this gap is significantly brighter and then the surrounding grain. And in fact, you can also make a false color image out of this, where you sort of bin the spectrum in 3 bins, and then attribute that intensity to blue, green, and red. And you can see indeed that this pore is really red, and the surrounding grain is purple. And this is also clear in the spectrum, where these numbers here indicate different positions, and these are the corresponding spectra. And at position 2, there's a very strong emission here in the red, and this is really characteristic for low quality quartz cement. And so it's well known that this has this type of color. This is also a well-known defect inside of quartz. And the more high quality grain has a strong blue component, which is not present in this cement, and which makes it easy to distinguish. So why is this relevant? And so you can, first of all, you can visualize the cement, and you can also quantify how much cement there is and how much cement has filled up the pore space, something relevant for oil and gas industry. But you can also try to establish the timing of geological events. So when was this cement, when did the cement came in? Particularly if you also look at fractures. So sometimes there's fractures in the crystals because there's a tectonic movement, for example, or and this you can time with respect to the cement infilling, because you can see whether the crack goes through the cement or not. And these types of things you can see really in these measurements. So here's another example. It's the same. It's actually the same type of thing. It's again a quartz grain, and these are panchromatic. This is a panchromatic CL image, and these are color filtered images, and they show the same thing. That these fractures are now, they're smaller than the ones I showed in the previous slide, but they're still healed by a different material. Again, quartz cement, and again you see this. This characteristic red versus purple color appear. This is really a textbook example of how you can use CL to image these types of fractures. So this is again a similar example, but this is just to show the effect of acceleration voltage. And so we again have a cracked grain. But we have done the experiment at 2 different acceleration voltages, 5 kilovolts and 15 kilovolts. And you can see the difference. And so at 5 kilovolts, you see much more surface topography in detail. And so the resolution, the spatial resolution is higher, and you're more surface sensitive. Whereas for 15 kilovolts, it's more uniform and more washed out, the result. You can also see that the intensity is much lower for the 5 kilovolts, because these y-axes here, they are to scale, which means that there's there's about a factor of 5, 3 to 5 difference between these two. So this was the first example, sedimentary of sedimentary rocks, and of course, so the examples that I show you can also extrapolate to other mineral types. And so I showed an example of quartz sandstone, but you can do all of the things I showed also for carbonates or the other types of rocks that I mentioned. And so please keep this in mind. Yeah, and so this is maybe one of the most well-known examples of cathodoluminescence in geology. It's the use for zircon imaging, and zircons are obviously very important for radiometric dating of rocks, and they have a strong zonation pattern always, or almost always, which is not possible really to see in SEM, as you can see here. You can see some detail in backscattering, but in cathodoluminescence, it's again really apparent because while the zircons grow, the defect structure and the changes because the composition changes, or the number of defects increases, which is all related to the way these things are grown. And cathodoluminescence is really the best technique to visualize these zonation patterns inside of these zircons. And here there's an example where you can see a beautiful zonation pattern and all of these fine lines, which are really related to the growth of these zircons. And of course, these zircons can also remelt over time, and which also again changes these patterns, and all of that can be interpreted. In the end, these types of measurements, they often act as a precursor for mass spectrometry measurements, where you want to identify an interesting zircon or an interesting area on a zircon for mass spectrometry to do, which is a very precise technique to get the exact isotope ratios. But it's a little bit time consuming and it's more expensive, and so cathodoluminescence is a really good precursor for that technique. Yes, and so you can image, of course, a lot of zircons, and it's quite easy because they are efficient CL emitters and also very robust. So you can also use high currents. And yeah, here's a mosaic of a lot of different types of zircons. And so you can see the zonation patterns. Sometimes you can see inclusions, like here, for example, which has clearly a different color than the surrounding zircon. In some cases, you can also see clear effects of radiation patterns, or radiation damage, sorry, that are present. Of course, you can also perform a spectroscopy on zircons. And here I show quite a characteristic example. And so zircons always have a broad defect luminescence band, which you roughly see here. But then you also see these finer peaks on top, and those are related to rare earth elements, which are present inside of the zircon. These rare earth elements have very well-defined peak positions, and they're quite sharp normally. And so often you can also identify which rare earth elements are present by looking at this. I have not gone through that exercise in this case, but it is possible often. And on a different position, the spectra can look different because the defect structure is different, and also the dopant concentration or even dopant type can vary. And so this is something you can look at using cathodoluminescence. Let's see. So I will briefly go back to questions. And so one question is whether there's an advantage to using angle-resolved imaging in zircons compared to other techniques like intensity mapping or hyperspectral imaging. I wouldn't really say so. I don't think angle-resolved imaging adds a lot in the case of zircons. I think nice hyperspectral imaging and intensity mapping is normally enough to do. I mean, unless you are maybe again looking at a specific defect type, but I think it is probably more interesting in other mineral types. Yes, and so here's another example, and so this is an example of sapphire. And these sapphires are courtesy of Jacqueline Wong from the University of Queensland, and we did a sort of a correlative study on these sapphires using both cathodoluminescence and mass spectrometry. And so sapphires, they're really dominated by extrinsic luminescence. So this is a very nice example, I think. And so we looked at different sapphires. And in this sapphire here, you see this cathodoluminescence spectrum. And this is completely dominated by chromium impurities. And yeah, chromium is a well-known light emitter in sapphire. And the concentration here is about 400 ppm, but even at that concentration, it already completely dominates the cathodoluminescence spectrum. And I think in some other sapphires here, the concentration was about 2 ppm, and you can still very clearly see it in the cathodoluminescence spectrum. And so in that case, you can detect ionic species well below the detection threshold for EDS, for example, or even WDS. And so in some particular cases, you can be very sensitive and measure very low concentrations. Yeah, and so and this is also in this case the case because the chromium peak is so sharp and has such a well-defined peak position that is easy to recognize. And in fact, the chromium emitter is so efficient that it's even used for lasers. In fact, for ruby lasers. And but this can change completely if you move to a different sapphire. And so in this case, the sapphire spectrum is completely dominated by titanium impurities. And in fact, those are also used for lasing. But in this case, the concentration is also somewhat higher. It's about 4,000 ppm. And so what I want to show next is also related to this experiment, is that this shows how careful you have to be with interpreting CL data. And so because we did mass spectrometry, we know for different positions what what different elements are present. And it is known that titanium is an efficient CL emitter in sapphire. And if you look here in this graph, you see that when the titanium concentration increases, the amplitude of the peak observed in CL also goes up, roughly speaking, say. But also, if you look at the iron concentration, you see that if the iron concentration increases, the CL intensity goes down. And this is because iron quenches the emission from the titanium in sapphire, and this is also known. But that means that if you see a reduction in your CL peak, it can either be because the titanium concentration was reduced or because the iron concentration increased. And so this shows that for quantitative measurements, you have to be careful about these things. But if you measure both concentrations, then it's still possible to do a correlation, of course. And so like sapphire and other high quality gemstones like diamond or so, cathodoluminescence is also very useful. You can image a lot of defects related to nitrogen, for example, and sometimes also learn about the origin or the melt from which it came, and those kind of things. Yes, and so the previous examples that I showed were really rocks that came from melts, but here I show something that comes from the living world, and so this is an example of a diatom, and these samples were given to us by Dr. Sten Liedman from the MPI in Bremen. And so these diatoms were really, when I measured them, they were taken out of a lake only a few weeks before, and so it's not really fossilized yet, and so it's not really geological research maybe in that sense. But I want to show that you can measure the cathodoluminescence on these anyway. And so you can very clearly, you can image them, and you can also very clearly see that the shell is silica based, and that's very clearly visible in the cathodoluminescence. And you can do the same for carbonate based organisms. And so this is an organism with a carbonate shell, and it has a characteristic carbonate spectrum, very blue. And of course, these types of things you can also do in fossilized materials. And in fact, there's also interest to look at bio minerals like bones and teeth, and which are more apatite based. In that case, it's also interesting to use cathodoluminescence either for biological research, but also for archaeology or paleontology. For these things, this is also relevant. Relevant technique. So these were the examples that I wanted to show. Keep in mind that they're just examples, and you can apply it to almost any rock type there is, but nevertheless, cathodoluminescence presents a fast and powerful technique to do microanalysis on rocks, and is complementary to other techniques that are already out there. And I think with the current sensitivity and precision that we are obtaining with our new CL systems, there are also some novel applications within reach. For example, minerals which are more metal rich, which were normally not bright enough to do cathodoluminescence emission, you could now still get results on. And new CL approaches from the hardware side can also broaden the scope and give new applications. And so the polarization resolved and the angle resolved imaging was already mentioned. Another new thing in the cathodoluminescence world is time resolved imaging, where you look at the time dynamics. And this is also very interesting in the context of defect analysis. As I mentioned, correlative imaging is, of course, an interesting way to go. And there's also a push towards more automated imaging, large area imaging, where you automatically scan a whole thin section, for example, and do automated segmentation and quantification of your sample, which is very beneficial for a more maybe industrialized form of cathodoluminescence. Okay, I will go back to the questions once more. Yes, and so the question is whether I have examples of the metal-rich materials that yield CL in geology, and so I do, but they're confidential for now, so my apologies. But if you have any ideas, please feel free to contact us also, because we are happy to try things. And we, as a company, we don't have access to like a wide range of minerals, but we will be happy to try things. But I can already tell that we already have some nice results on minerals which are not studied a lot because they're deemed too dark in CL. But maybe that can be part of a next webinar. All right, and so I think if there are no further questions, I will refer you to our websites for further information. And so I hope that you enjoyed it. And I think maybe I will give the word back to Kamran now.
Thanks very much, Tom. And thanks very much, all the attendees. I hope you all enjoyed the webinar. And thank you very much for all the questions. I'll be sending some feedback forms in the next few days. We've made these forms very, very easy actually for you guys, so you can spend just maybe 30 seconds and just press a button and then the form will be sent to us. we will appreciate really if you do that, because it will help us to bring better topics and do better in the next webinars. So before finishing, I have actually one just more question for Tom. So if we want to use the Spark only for geological applications, what configuration of the Spark do you suggest?
Yeah, and so yeah, it depends a little bit on the exact application also within geology. And so we have a basic system with which you can do more basic system with which you can do intensity mapping only. And that is useful for doing a lot of the quartz imaging and the zircon imaging, for example. But you cannot get any spectroscopic detail. And then, if you're interested in that, then you can take the more advanced system, which you can also do the spectroscopy. And the spectroscopy system can also do the intensity mapping, by the way. And so it's an extension of the system. And this can also be amended with polarization resolved and angle resolved cathodoluminescence, if that is also interesting.
So we can start easily with the basic system and then upgrade in future when we see the need is there.
Yes, that is possible. Yeah, we have a system in which you can exchange your system easily for a hyperspectral system, and so that is highly encouraged. If you want to start out more simply and then later on expand, that's possible. In general, the systems that we have are very modular, and so there's always possibilities to expand it later on with new optics or with new gratings for different spectroscopy measurements, and even you can also purchase a more expensive camera later on, which is better. And so there's a lot of possibilities to improve the system later on also. So you're not stuck with a single system for a long time if you don't want to.
And just last question: any specific requirement on the SEM part, like?
Well, normally not really. I think the main requirement is to have some space, and so there has to be at least one available port, which is looking at the pole piece, because that is where the collection optic is. And inside of the chamber, there has to be some room to mount the collection optics, but 90% of the SEMs they are compatible with the system, and we can always look at your case, and so we have engineers that can look at the drawings, so we can establish whether the normal system fits, and if it doesn't, there's even a possibility maybe to make something customized. But normally the standard system covers, I think, 90% of the SEMs from all the different vendors.
So we have another question actually that came up right now about the software associated with the system.
Oh yeah, let me look. Yeah. Okay. So the software is free, and so so there are no licenses or anything, and so you can interrogate the data also on your own computer if you want with the data analysis tools that we have. And so the software includes all the things you need for imaging, and so you can do the scanning, region of interest selection, drift correction. The data is saved in different formats, all of which are open. You can export the data into different image formats, and then that's very easy. And so there's, as I mentioned, there's a special viewer that you can use everywhere, and which you can also use to export the data. And the software is also continuously improved, and updates are free. And so in that sense, you have access to all things you want from the software perspective, I would say. Yeah.
Great. Thank you very much for all the answers. And again, thanks everyone for attending and being with us. So next webinar will be in a month's time. Please have a look at the AXT webinar page. So the next is on the correlative electron microscopy with super resolution fluorescence microscopy. If you have any interest in that regard, please just register and be with us again. And I wish you a very good afternoon and see you hopefully next time. Bye.